Okay, in this video we're going to be analysing those key concepts in a slightly different perspective. We're going to be looking at this thing called a motion graph. And a motion graph is really moving away from the concept of an equation and looking more at a sort of more visual representation of what's actually going on and allowing us to really paint a clear picture of what's happening. So when we have a motion graph, we can sort of have two key different motion graphs that we're going to be analysing. The first one is what we would refer as a displacement time graph. And what that means is that on one axis we have displacement, which will be on the y-axis, and on the x-axis we have time. Now the other type of graph that we're really going to focus on is a velocity time graph, which again means that velocity is on the y-axis and time is on the x-axis. And what we'll be able to do is tell a bit of a story about what's actually going on here. So we're just going to go through some examples and try and pull apart what information you can take from these. So firstly, if I were to look at a displacement time graph that looked like that, and I'll just represent because that's actually meant to be a horizontal line. So if I've got a horizontal line and I was sort of asked, well, what is this actually telling me? What this type of graph is telling me is that this object is actually not moving. And the reason behind that is that, one, it's stationary, and two, we can work that out by the fact that no matter what this value is, so if we said, for example, this was 20 meters, what this is saying is that after 1 second, and after 2 seconds, and after 3 seconds, that object is still at a displacement point of 20 meters. And it means that it is simply not moving. Okay, so this would be an example of a stationary object, which is represented by our displacement time graph. If I pull it apart and we look at another sort of fairly basic example, and we said here we've got displacement and time again, then what this type of graph would be representing is a constant velocity forwards. Okay. Now the reason we can sort of say that is that firstly this line here is a straight line, and what that is telling me is that if I'm looking at how the displacement is increasing with respect to time, so if I look at 1 second and I said, for example, that it had moved forward 2 meters, and then after 2 seconds, I said it had moved forward 4 meters, you can see that after every second it's going up at a rate of 2 meters. And as a result of that, we can say that it's got a constant velocity. Now, the fact that the graph is going upwards is probably an indication that it's going forwards. However, we do need to be careful because sometimes you'll need to read the question to get more information about what's forwards, what's backwards, what's up, what's down, what's positive, what's negative. So this is generally what we're sort of looking at here. Now, the other thing you might be able to interpret from that is that when I say it's moving at a constant velocity, what that is also represented by is the fact that the slope of this graph is actually representing the average velocity. Now, the reason behind that is if you look at the slope of the graph, what we're saying here is that the slope of any graph would be equal to rise over run. Hopefully we know that from our work in maths, which could also be represented by y2 take y1 over x2 take x1. And if you look at what's on the y-axis, we've got displacement. And if you look at what's on the x-axis, we have got time. So what that's telling me is that the slope is basically equal to the same thing as displacement divided by time. Now, one thing that we've already mentioned in one of the videos we've looked at is that velocity, or average velocity, is equal to displacement divided by time. Okay, we said that speed is equal to distance over time and velocity is equal to displacement over time. And because velocity is equal to displacement over time and slope is equal to displacement over time, therefore we can say that slope and velocity are the same thing. And because that line is straight, therefore we can say that it is a constant velocity. All right, so this idea of an average can kind of disappear here because it's constant as it's represented by a straight line. If it was curved, then we might need to look at things slightly differently. Now, we don't just need to look at straightforward examples like that. We can make it a little bit more complex. So if I again go and say we've got a displacement time graph here, and let's say I'm going to draw up something like this. And I was asked to sort of tell the story of what's happening in this graph. Well, hopefully you can see there's kind of three clear things that are occurring in this graph. In this first section here, which is the part going up, if I call that sort of like part A, then part A has got a constant velocity forwards. And that's represented by that straight line, which is going up, as we mentioned before. and the fact that it is a constant rate of displacement compared to time. If I call this sort of section here part B, then you can see in that part that it is a stationary object, and that's because the displacement is not changing with respect to time. It's standing still. We mentioned that before. And if I called this part part C, then what I'm saying here is that in this part it's sort of going backwards. All right, and I'll explain why in a second. It's doing that at a constant rate. And then the other thing to probably note in this type of graph is that the motion started in this position and it's finished at the same position because it's returned to the original starting position. The graph hasn't gone above or below the horizontal axes. So what this is also telling me is that the object is starting and stopping at the same point. Okay, so there's lots of different things. We can really tell a story from what we've actually seen in the graph, and that's quite a useful thing for us to be able to do. Now, if I sort of go right back to the start of this conversation and now start looking at velocity time graphs, again, if I start with that very basic sort of example of a line going horizontally across, what this is representing this time, though, is a constant velocity. Now, it's very important to note this because previously for a displacement time graph, when we had a horizontal line, we said that that was saying that the object wasn't moving. For a velocity time graph, that does not necessarily have to be the case. In fact, if you see here, if I labeled this 15, for example, what this means is that at every time point in time here, the velocity is always 15, all right? It's not 0, so the object is still moving. So this is a constant velocity if we have a horizontal line. It could potentially be 0, but it doesn't have to be, all right? Just so we're aware of that. If we look at the other sort of fairly basic example that we were sort of looking at before, this time for velocity time, so if I have like a straight line sort of looking like that, then what we would say in this scenario is that this is a constant acceleration. It's a very, very similar story to what we were just going through before. So the reason we would say this is, again, if I sort of remember, well, what's the deal with slope? We said that slope is equal to rise over run. And I said, what's on the y-axis? Well, the answer is velocity. What's on the x-axis? The answer is time. And then I sort of said, okay, well, remember, what do we know about acceleration so far? Well, we know that acceleration is the change in velocity divided by time. So we've got velocity over time and we've got velocity over time, which means that slope and acceleration are the same thing. And again, because this is a straight line, we can say that it is constant. So the slope of a velocity time graph is being represented by the acceleration. So for this graph, we are saying that there is a constant acceleration that we are dealing with. And then I guess similar to what we did before, if we tried to tell a bit of a story about this, so if I sort of said, let me write up the axes first, if this was velocity and that was time, and then we looked at it and we said, okay, this one's going to do something like this. And again, I broke it into those 3 segments. So I'd say, well, in this part A and part B and part C, in part A, we're moving forwards with a constant acceleration because that's what we just went through. So this might be, for example, a car sitting at a traffic light and we are not moving. The velocity is increased from 0 to a certain value, so it might have gone from 0 to say 10, and it's done that at a constant rate because this is a straight line. In part B, we have got a constant velocity. So that doesn't mean we are not moving. In fact, what it would mean here is that we've accelerated to a point of 10 meters per second, and now we're moving at that. And then in part C, we have again begun to move with constant acceleration. So it might have been with cars sitting at the traffic lights here, it's accelerating to a velocity. We then get stuck behind another car, so we do that velocity for a while, and then we get past that car and start to accelerate and start to move again. So motion graphs can tell us a really intricate story of what's actually going on with this type of motion. A much more probably thorough examination than what we can see through equations, but you can see that they do link quite nicely to equations as well. We saw that a few times throughout. So that's the story with motion graphs.